This talk is an introduction to CFCs and how they interact with the ozone layer. CFCs stands for chloro, fluoro, carbons. CFCs for short, because they only consist of three different types of atom: chlorine, fluorine, and carbon. And these chemicals were originally introduced because of some amazing properties. They were non-toxic, they were non-flammable, they were stable, and they were gases. And that was very important because you need these properties for refrigerants. And the fact that they were non-toxic, non-flammable, and stable meant they were much better than the chemicals that they replaced, such as ammonia. So they were introduced as a wonder chemical. They could be used as refrigerants. They had none of the safety concerns or toxicity concerns of previous chemicals. And for a long time, no one had any idea they could cause possible problems. And that is because of this one fact here, because they are so stable. Because they're so stable, that meant they could stay in the troposphere, that lower layer of the atmosphere, for a long time. And in the troposphere, there is no UV light which might decompose them. So once they were released from the troposphere, they slowly built up in the troposphere, and slowly they started to diffuse up into the stratosphere. Now the problem is, once they diffused into the stratosphere and reached the ozone layer, they now encountered UV light, because while they're in the troposphere, they were being protected by the ozone layer from UV light. But as soon as they reached the stratosphere, then they started getting hit by UV light. And when the CFCs were hit by UV light, they started to decompose. Their decomposition produced something called chlorine-free radicals, and that's what's caused the ozone layer damage. So let's look at an example chemical situation of how these CFCs caused ozone layer damage and eventually led to the ozone hole that appears over the Antarctic in spring. An example CFC, as a nice simple example, CF3Cl, chlorotrifluoromethane. This is an example of a CFC. It only contains carbon, fluorine, and chlorine atoms. Now, when this particular chemical made its way into the stratosphere and encountered UV light, it decomposed. And what it formed, or one of the species it formed, was a chlorine-free radical, a free chlorine atom with an unpaired electron, making it very reactive. Now, chlorine-free radicals in the stratosphere encountered ozone, and when chlorine-free radicals, which are reactive themselves, encounter ozone, which is a reactive molecule, they react. And what happened was the chlorine-free radical removed one of the oxygens from the ozone molecule, so that it was no longer ozone. It formed this thing called chlorine oxide and oxygen. But in one of our previous talks, we learnt that in the ozone layer, there's an equilibrium between ozone, oxygen, and oxygen-free radicals. So there was also oxygen-free radicals in the stratosphere, in the ozone layer as well. And oxygen-free radicals and this chlorine oxide were both reactive chemicals. And chlorine oxide reacts with oxygen-free radicals to turn back into a chlorine-free radical and oxygen. And what you can see here is we've reformed the chlorine-free radical. And that chlorine-free radical was free to go and start the process all over again. And it turns out that for every one chlorine-free radical can decompose approximately 10,000 ozone molecules. So effectively, the chlorine-free radical in this cycle anyway, the chlorine-free radical was a catalyst for ozone decomposition. And that led to ozone depletion and ozone thinning. But we said it only decomposed 10,000 ozone molecules. It wasn't a perfect catalyst because eventually it was consumed. It wasn't consumed by this reaction, it was consumed by some other reactions that take place in the upper atmosphere. One of them being that chlorine oxide can react with nitrogen dioxide in the atmosphere. So this reaction can stop the cycle. And that's one way the cycle is stopped, because that chemical there, I think it's chlorine nitrate, that does no longer have any impact on the ozone layer. Another way that this can be stopped is if the chlorine-free radical itself reacts with some methane in the atmosphere. When it reacts with the methane in the atmosphere, we produce hydrogen chloride, and this free radical as well, neither of which have any impact on the ozone layer. So because of these two reactions, the chlorine doesn't completely decimate the ozone layer, but even still the volume of CFCs that were put into the atmosphere has had a serious impact on the ozone layer.